Black holes, among the most perplexing and extraordinary phenomena in the cosmos, continue to captivate and challenge both observational astronomers and theoretical physicists alike. These celestial entities, defined by their immense gravitational force and total absence of emitted light or energy, represent the limits of current scientific understanding, a frontier where the known laws of physics begin to collapse. First predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity, black holes were long regarded as theoretical oddities. That perception shifted dramatically during the mid-20th century as advancing technologies enabled scientists to detect indirect evidence of their existence. A landmark moment occurred in the 1960s when astronomers, observing the Cygnus star system, noticed a luminous blue star emitting intense X-rays while orbiting an unseen massive object. This object, later identified as Cygnus X1, defied traditional explanations and was ultimately confirmed to be a black hole. This discovery offered concrete evidence that black holes were not just mathematical abstractions but real components of our universe. Located approximately 6,000 light-years from Earth, Cygnus X1 exhibits extraordinary properties. Its density and gravitational pull are so extreme that not even light can escape its grasp. This characteristic led to the term black hole, a name that aptly captures the enigmatic nature of these cosmic voids. Since then, research has uncovered an astonishing variety of black holes scattered across the universe. Estimates suggest that the Milky Way alone may contain over 100 million of them. Despite their elusiveness, scientists have identified numerous likely black hole candidates in our galactic neighborhood. These range from stellar mass black holes, formed from the remnants of massive collapsed stars, to supermassive black holes that anchor the cores of galaxies. Their influence extends far beyond their immediate vicinity, shaping galactic evolution and altering the trajectories of nearby celestial bodies. Matter that strays too close to a black hole inevitably crosses the event horizon, the critical boundary beyond which escape is impossible. Within this region, gravitational forces become so intense that objects experience extreme tidal stretching, an effect known as spaghettification. The gradient in gravitational pull across an object's length becomes so vast that it is elongated into thin strands, ultimately torn apart and absorbed by the singularity at the core. Black holes offer a natural laboratory for testing the boundaries of physics, yet they remain deeply mysterious. The pursuit of understanding their complex nature is driven by humanity's desire to grasp the true architecture of space-time and the behavior of gravity on the grandest scales. These cosmic enigmas continue to inspire both awe and rigorous inquiry, challenging researchers to push the frontiers of theoretical science. Even though the nearest confirmed black hole lies about 1,500 light-years from Earth, their potential influence prompts ongoing speculation. In 2021, astronomers achieved a historic milestone by capturing the first definitive image of a black hole, specifically, the one at the heart of the M87 galaxy. This groundbreaking photograph offered vital insights into black hole structure and behavior, challenging the simplistic notion of black holes as empty voids. Careful analysis and imaging revealed that black holes consist of multiple layers. The outermost layer, the event horizon, marks the boundary where all paths lead inward. Within this lies the photon sphere, a region where light orbits the black hole due to its intense gravitational pull. Any photon entering this domain becomes trapped in perpetual motion. At the center lies the singularity, a point of infinite density where known physical laws break down and spacetime itself becomes warped beyond recognition. These internal components highlight the complexity and uniqueness of black holes. While many follow a general structural model, each exhibits individual properties and behaviors that defy simple classification. Traditional investigative methods often fall short, forcing scientists to adopt innovative approaches. Since no probe can survive a descent into a black hole, indirect observation, through radiation, gravitational effects, and simulations, remains the principal means of study. Nonetheless, researchers persist with unwavering resolve. Theories on black hole formation range from the collapse of massive stars to colossal cosmic collisions. A prominent example is NASA's ongoing study of the M87 galaxy's core, which strongly suggests the presence of a supermassive black hole with immense gravitational influence over a vast region of space. Among the more profound developments in black hole theory was physicist Roy Kerr's 1963 model of rotating black holes. Kerr introduced the concept of the ergosphere, a region surrounding a spinning black hole where spacetime is dragged around at near light speeds. This bizarre domain demonstrated properties inconsistent with classical physics, hinting at deeper mysteries hidden within black holes. One particularly captivating implication of Kerr's work was the theoretical existence of Einstein-Rosen bridges, or wormholes, hypothetical tunnels through spacetime that might connect distant regions of the universe or even parallel dimensions. These concepts emerge from general relativity's description of how massive objects bend the fabric of spacetime. Wormholes, if stable, could theoretically function as shortcuts across vast cosmic distances, raising the tantalizing possibility of faster-than-light travel. Yet, wormholes remain speculative. Questions about their stability, susceptibility to quantum fluctuations, and exposure to high-energy radiation pose significant challenges. Moreover, Einstein's own equations place stringent limits on the speed of travel through spacetime, meaning that even if wormholes could exist, they might not allow traversal at superluminal speeds. Despite these obstacles, wormholes persist as powerful metaphors for scientific creativity, offering glimpses into realities far removed from everyday experience. The ongoing quest for a unified theory that bridges general relativity with quantum mechanics has spurred efforts to develop a theory of everything. At the forefront of this search is the celebrated physicist Michio Kaku, whose pioneering work in superstring theory represents a radical shift from classical paradigms. This theory proposes that the fundamental constituents of matter are not point-like particles but tiny vibrating strings. Each string oscillates at a specific frequency, giving rise to the variety of particles and forces observed in nature. Within this framework, the universe resembles a vast symphony of vibrations, each particle a note played by a string vibrating in multidimensional space. One of the most striking features of superstring theory is its ability to incorporate exotic phenomena like black holes and wormholes into a single elegant model. However, this model demands more than the familiar four dimensions. It introduces additional, hidden dimensions compacted into tiny, imperceptible scales. These extra dimensions can be likened to a fish living on the surface of a pond, unaware of the third dimension above. Similarly, we may be blind to the true architecture of reality, existing within a multidimensional cosmos that subtly shapes everything we observe. Though we cannot perceive these hidden dimensions directly, they may play a crucial role in the evolution of the universe and the distribution of matter. Superstring theory has reinvigorated theoretical physics by revealing deep connections between mathematics and the physical world. It has also fostered unprecedented collaboration across disciplines, showcasing the interplay between abstract theory and empirical investigation. Despite its elegance, however, superstring theory remains difficult to test experimentally due to the inaccessibility of the predicted dimensions and the incredibly small scale at which strings operate. Nonetheless, the theory continues to inspire physicists, pushing the boundaries of human understanding. As we delve further into the landscape of theoretical physics, guided by the promise of string theory, we inch closer to solving some of the universe's most profound mysteries. The quest to understand quantum black holes stands as one of the most formidable challenges in modern science. These objects, which merge gravitational collapse with quantum uncertainty, have puzzled researchers for decades. Edward Whitten of the Institute for Advanced Study once remarked that, "Superstring theory is 21st-century physics that accidentally arrived in the 20th century." His observation underscores the vast intellectual terrain yet to be explored. Recent breakthroughs, however, have reignited optimism. Several independent research teams have achieved promising results suggesting that string theory might offer a complete description of black holes, particularly in simplified two-dimensional models. While these findings mark significant progress, the road to a fully unified theory remains complex and uncertain. Ultimately, the study of black holes reshapes how we view the universe. It compels us to question the nature of time, space, and existence itself. Interactions between black holes and other celestial phenomena, such as neutron stars, gravitational waves, and gamma-ray bursts, continue to reveal the intricate mechanisms that sculpt the cosmos. In these shadowy realms where physics teeters on the brink of the unknown, we find not only challenges but also profound beauty, a reflection of humanity's enduring quest to understand the universe and our place within it.